Okay, this is Physics Lab 4, where we're going to look at an oscillating motion. The purpose of this lab was to analyze and predict the motion of an object swinging from a fixed point while also oscillating on a spring. It was also to calculate the spring force and the gravity force that can be added up to find the net force. And it was also to test the energy principle, to see how the potential energy of the spring, the gravitational potential energy, kinetic energy of the mass change during oscillations. My calculated and experimental findings were very similar and did support the correctness of the energy principle. Here are some relevant equations that we're going to use in this lab. For this lab, we chose a system to be the mass and the spring and the earth. That way, the change in energy of the system is equal to 0. Using these equations, we also found the spring constant and the relaxed length of the spring when we measured the mass and the length with the mass hanging off of the spring at rest. Here is some of the data I got from Tracker. Unfortunately, my video it was saved and won't come back, but this is the X versus time. This is some of the data, and here's my tracking it. Okay. Let's see. Okay, for my VPython code, I put in the mass at 0.402 kilograms. The position was my initial position, as you can see here. And then the initial velocity is 0 because it's at rest initially. Then after that, we put a time step that was larger than what we had in the frames. Put it in the gravitational acceleration, the spring constant that we found before, and the relaxed length of the spring that we also found before. To find the length, you use the ball's position minus the spring's position. And then to find the unit vector for length, you just do the length over the magnitude of the length, because length is a vector. And then to find the stretch of the spring, you do the magnitude of the length minus the relaxed length. Here we have our equations for kinetic energy, gravitational potential energy, and the potential energy of the spring, which I had on one of the slides before. This gives you the initial energies. The force of gravity is the mass of the ball times the acceleration due to gravity times the vector 0, -1, 0, because it goes in the negative y direction. Here's the force of the spring, which is the negative spring constant times s, the distance between the length and the relaxed length of the spring, and L hat, giving it direction. F net is equal to the force of gravity plus the force of the spring, because they're the only two forces acting upon it. We use Newton's second law to find the ball's new velocity. So we do final velocity is equal to initial velocity plus F net divided by the ball's mass times delta t. And then using that new velocity, we can find the ball's position using the final position is equal to the initial position plus the velocity times delta t. Then we use the same for here to update the spring force. And then here we're updating the energy by doing the change in K is equal to final minus initial, and same for the potential energies. We then use these arrows to show the force of spring and the force of gravity. And here, let me run this. You can see how the spring moved, and here are how the energies were changing. Then, to compare the our results with what we calculated, we used this and just changed it to graph the y position of the calculated and actual results. So here we got, which you can see the red and blue. The red is our experimental and the blue is our calculated. They stay pretty similar. The red one jumps a little bit and is a tiny bit off at certain points, like right here. But overall, they're pretty similar, as you can see from this graph. One of the reasons why it might have been a bit different was because there was air resistance that we weren't accounting for, and the spring could have possibly, or the mass could have touched the board, which would add a contact force that we weren't accounting for. Here I graphed the x position versus time and the y position versus time to find the average periods. The average x period was a little larger than the average y period, which is why the mass gets a strange pretzel shape of motion. And the disparity is caused by a difference in the forces acting in those directions, because the net force is not zero in this lab, or even constant. So that's why the periods are different. Overall, I thought the lab was a success, and I predicted the motion well.